Hello, welcome back to this course on differentiable manifolds. This is a second video devoted to symplectic geometry. Did you enjoy the last video? Reply the question up there. Okay, so the purpose of this video is, in the last video, what we did was just to introduce the definition of what is a symplectic manifold, and we gave some motivation coming from Hamilton's equation. Why do we need a form to be closed? Why do we need a certain form to be non-degenerate, etc. Now, it's the afternoon, and here at the beginning of the afternoon in my wonderful library, you see all these books there. By the way, did you see this green book there? Let me take it for you. Let me take it for you. Wow, yeah, that's this book. That's Symplectic Techniques in Physics. This is a book that I recommend for this part, okay? Well, you know, in the notes that we are writing with Paul Mir and Cedric Ohms, you will find the notes of the course, the plain notes of the course, which I'm quite proud of, but of course, this needs to be refined because this is the first year we are providing notes. And if you, sometimes you write me emails to ask me which bibliography do you recommend for this part, okay? Some of you have done this in the previous chapter. For the introduction to symplectic geometry, that's a great book. That's a book by Guillemin and Stenberg. And well, you can find it in the library, but oops, well, the library with difficult times, okay? Maybe you have it, maybe you have access to this book, maybe you can buy it through Amazon, okay? Well, it's true that Victor Guillemin is my collaborator. I'm not here to sell this book, but this is an awesome book, and it provides a lot of nice examples from it. For instance, nice motivation to study symplectic forms, for instance, from optics, etc. Some of you have used this book for the final essay of the course. Kevin is going to give, I hope, a wonderful talk about the relation with optics, and you will see this on the third week of May when we have the presentation of the books. Okay, this was just a big distraction by looking at the books in the shelves, but okay, this is the bibliography for this part. Let's forget about this. And now I finished last section with two questions. Can the product of two spheres, because the conclusion is that, well, a symplectic form is just is given, I mean, a symplectic manifold is given by a pair, a manifold, and a two form, and the two form governs the geometry of the manifold, okay? And the conclusion is that we needed this form to be non-degenerate and closed. The motivation to consider non-degenerate two forms was crystal clear. It comes from looking at Hamilton's equations and looking at the solution to a certain equation. We needed to solve a certain equation where we had the differential of Hamilton's function, okay? So the motivation was crystal clear about non-degeneracy. And well, the thing is that the form that we were using was indeed exact. All of you know that exact one forms are closed. But of course, you know that not all closed forms are exact. That's what cohomology is for, okay? So I'm going to start this video showing you that we need that if we have a compact manifold, we cannot have symplectic forms that are exact, okay? This is a nice application of Stokes' theorem. And from that theorem, we'll get a cohomological constraint for free. We'll see that the symplectic form defines a class in the second cohomology clause, because this is closed. Therefore, it defines a class in the rank cohomology. And this class is different from zero if the manifold is compact. Therefore, we get for free an answer to one of the questions we were asking, which is can a four-dimensional sphere be symplectic? Voila! This tells us that a four-dimensional sphere cannot be symplectic because the second cohomology group is zero, okay? Whereas in the two sphere, this works. Indeed, the only sphere that can be symplectic is the two-dimensional sphere. This was one of the questions. And the second question is, can the product of two spheres be symplectic? Of course, but this is very trivial observation that if I have two symplectic manifolds and I make a product, this is again a symplectic manifold. So stay tuned. I'm going to prove this result. I'm going to give this characterization, this topological characterization, or if you want, abstractions that a certain manifold needs to have to admit a symplectic form. So obvious abstraction is that the second cohomology group doesn't vanish if the manifold is compact. And then I told you that I would talk about local and global classification. I'm going to do two things in this video. That's great. First thing, I'm going to prove that locally all symplectic manifolds look the same. I'm going to prove the Darboux theorem, and I'm going to do this with the force of the Moser's path method. I'm talking about Moser. Moser is Jürgen Moser. I'm going to try to link a video about Moser there. And Moser, indeed, he wrote a wonderful paper in which he was trying to classify Riemannian structures on a compact manifold, and he proved that the only invariant was the volume. And you say, well, you are talking about Riemannian geometry now, but in dimension 2, remember that that's the same. It's the same to have a volume form that to have an area form. An area form is a symplectic form. It's the same. Therefore, this theorem gives us for free a global classification of symplectic surfaces. I hope you enjoyed this video. Again, because I have a problem with the other computer, I'm going to have to take out the video here and use it to write. See you later. Okay, so first thing I do is to share with you okay, that's the last, that's indeed the last, this is exactly where we stopped in the last video, okay? That was the motivation. And remember, we start with the definition, recalling the definition of symplectic manifold and the definition of symplectic form. To form on a manifold is called symplectic if it's closed and non-degenerate. All right, the condition of non-degenerate became obvious from the fact that we needed to have a solution to this equation here. All right, but now, okay, we started, well, we observed at the very end of the last video that we had a non-degeneracy condition reloaded that we could check with the matrix, and as a conclusion, all symplectic manifolds had to be even dimensional. And that's an important consequence, and they had to be orientable because non-degeneracy could be seen as the fact of being a volume form. So then we start, that's an important consequence. So for instance, a projective space, okay, can never be a symplectic manifold. A Klein bottle can never be a symplectic manifold. And we ended with this observation that all two-dimensional manifolds, I said all two-dimensional, all orientable surfaces, okay, which are two-dimensional manifolds, are symplectic manifolds. What about higher dimension? This was the end of my talk. Okay, so now I'm going to answer these two questions. The first one is pretty trivial. It's an exercise. Okay, so let me start by answering the questions, and I'm going to choose green. Okay, what about green? Okay, so this is question 1. Question 2, the answer is yes. Why? Because if I have two symplectic manifolds, I understand that the symplectic manifold is a pair of manifold endowed with a symplectic form, with a closed loop form. Okay, so if this is symplectic, okay, and this is symplectic, then the product, it's again symplectic with the sum of the two forms, understanding that you are going to have a trivial projection that sometimes we don't write it because, right, it's quite boring. It's pi1 and pi2. at the projections on M1 and M2. And of course, I can, I can become very sophisticated. Instead of saying the sum, I just take this. I just pull back the symplectic forms. And it's obvious to check that this guy is going to be closed. So this is an exercise. Check that this is closed, all right, and non-degenerate. So in particular, because the sphere with any area form is going to be symplectic, in particular, this is symplectic. So I can just take a product of two of them, and this is going to be symplectic as an application of this super easy exercise that I hope that you already saw. When I say area form, you can even think that you, if you express this in coordinates, I may consider cylindrical coordinates. I have been using the notation of height and theta. And in this notation of cylindrical coordinates, the symplectic form, I can think of this in this term. Okay, I can also compute it from R3, in standard coordinates and change to cylindrical coordinates. Okay, and now let me address. I want to solve the second question. What about question 2? What about S4? Okay, so the first thing I'm gonna do is to before this, I'm going to answer another question that I did in the former video, but by proving this property, I will also be addressing this question. So it's not that I'm changing the topic, I'm exactly talking about the same, all right? Okay, which is the following remark. Okay, let M be compact and assume that I have this, and assume that I have omega, it's a two form, differential two form, which is non-degenerate. These are the assumptions. Then omega, okay, if I have this is non-degenerate, then omega, this is compact, this is non-degenerate, then omega cannot be exact. Okay, let's prove this. Let's change color. What about fuchsia? Well, or no, this purple. Proof. Assume omega exact. Then this means that I can write omega as the differential of beta. Okay, for a certain beta, omega is a 2 form, and this is a 1 form. All right. On the other hand, as we saw before, omega n is a volume form. Okay, so assume that you have this form, because non-degeneracy, this is equivalent to omega n be a volume form. This is something we saw. Therefore, we have on one hand, because this is a volume form, when I integrate over m, this is strictly positive. On the other hand, I'm going to leave as an exercise, and I'm going to leave this in a different color, so you know this is an exercise. Maybe this color, exercise. I mean, this is just when I say an exercise, this is not a difficult exercise, this is a computation. That if omega is the differential of beta, then omega n can be written as the differential of beta wedge omega n minus 1. Formula which I'm going to use exactly now. Okay, so I use this formula here. I go back to my purple color, and I write this as the integral over m, therefore, of the differential of the differential of beta wedge omega n minus 1, right? And now it's time, of course, when I don't put anything, I mean, I'm using my volume form. I'm integrating over my volume form. I have a measure from my mind. Now I call Stokes formula. Of course, I'm assuming I didn't say anything. If I don't say anything, this manifold is without boundary. Okay, sorry, that's the other way around. Say without boundary. So the boundary of this guy is the empty set. All right. Okay. So because of Stokes' theorem, now this is just the integral over the boundary of M of this form, which is an n minus 1 form. Okay? Because omega is a 2 form. So sorry, this is a 2n form, and this is a 2n minus 1 form. So I can integrate it there. But because the boundary is empty, this is 0, which is a contradiction between this thing. So we reach a contradiction. Therefore, corollary of this remark, any symplectic form on a compact manifold a symplectic form maybe. Is never exact. That's the corollary. So from this corollary, I can do two things. Well, the first thing I can do, well, this is an important corollary, which tells me that this form can never be exact. So now I can look back to the question that I did, the exercise, which I agree is not easy. Is S4, can S4 be symplectic manifold? Remember that S4 is a guy which was cannot be either as a Lie group. Remember that the only fields which were Lie groups were S1, S3, okay, and S7 because of the octonions. So what happens with the poor S4? Well, the poor S4 cannot be symplectic. That's too bad. So I'm going to put this as a corollary. The only spheres that can be symplectic are the two-dimensional spheres. In particular, S4 cannot be symplectic. Okay, what is the relation between the fact that a symplectic form on a compact manifold is never exact to the fact that the spheres of dimension higher than 2 and even dimensional cannot be symplectic? Well, the answer is the connection is given by the RAM cohomology. And the RAM cohomology is telling me that a very interesting fact. If I have a symplectic form, because it's closed, that's important, I can talk about the class of omega. This defines a cocycle. All right, a cocycle in the RAM cohomology. Therefore, sorry, I was too quick. Sorry. I don't know why I said 0. I was too quick. This defines, okay. This defines a class. I'm going to change the color. I like to change colors. What about this nice color? Okay, this defines a class
Okay, and now important remark, because maybe you don't remember the rank homology, the class is 0 even only if omega is exact. All right, that's important. The class of a cohomology class is 0. It means that that any representative is exact. Okay, omega is a 2 form, therefore this exactness tells me that there exists a 1 form alpha. Here alpha is a 1 form on the manifold, on this compact manifold, such that omega is the differential of alpha. Okay, now let's recapitulate what we've seen. Okay, now we see again. So this means that if I have exact form, the class is 0. Is 0 even only if. Okay, therefore, because I know that because of this corollary, okay, because a symplectic manifold, a symplectic form and a compact manifold is never exact, the conclusion is that the symplectic, that if M is compact, the conclusion that we have just seen is that the class of omega is different from 0, because this condition equal to 0 means that it's exact. Okay, so therefore this means that the second cohomology group of the manifold is different from 0. That's exactly the condition. Okay, which now I can state as a corollary or as a theorem, as you want. If I have a symplectic manifold, compact symplectic manifold, then the second cohomology class is different from 0. Therefore, all the spheres, this implies that S2n is not symplectic for n greater or equal than 2. Okay, that's the conclusion that we get from this guy. So I have answered your questions. Okay, well, I have answered the previous questions. Now we completely understand why we ask that, because of this condition, that's the reason why we ask for a symplectic form to be closed and not to be exact, because if we want to work on a compact manifold, which is quite reasonable if you are a geometer, then you're not going to be able to do anything because there are none. Okay, so now we've seen, okay, all this is about abstractions for a topological manifold to admit a symplectic form. Okay, now the next step is now assume that your manifold has a symplectic form. Can you classify? So that's the next step that we are going to see in this video. Okay, and that's the last thing we are going to see in this video, because videos need to be a bit shorter. So next goal. So previous goal is topological abstractions. We could say these are topological abstractions. And we could go on. There are, of course, tons of topological abstractions, but this was like just like a little introduction to the subject. So next goal, now assume we have a manifold already with our symplectic form. Question. Can we classify omega, the manifold, globally or locally? The first one, it's a very hard question, and I'm only going to address this in dimension 2. Why? Because this is just the internet. But I'm going to classify all of them locally. What does it mean, classify? Well, classify means to put in boxes. That's what it means to classify, right? Classify is to put things inside some nice boxes. So I have different boxes of different colors. Okay, I have purple, fuchsia boxes. I have blue boxes. Okay, I have different boxes. So classify means to put things in boxes, and in such a way that if two things are on the same box, they are the same. They are the same, or they are equivalent in the sense that there exists a differomorphism taking one to the other. So for us, classification means the following. Means to decide, well, this color is very nice, but you cannot see it, right? So I'll have to just change to this. Decide when two I went too fancy with the colors. Decide when two symplectic manifolds are the same. Okay. Well, and what does it mean the same? It means the same. Okay, it means the same. Okay, it means that there exists, it means equivalent. And equivalence is there exists a diffeomorphism from the manifold, from one manifold to the other. Okay. Diffeo that takes one form, omega2 to omega1. That's the equivalence relation I'm going to consider. So that's when I say that two symplectic forms are equivalent, okay? Or this equivalence, I could say it has a name, okay? This is a definition, and these are called symplectomorphic. I'm going to choose then these manifolds are called symplectomorphic. Okay, so first thing we're gonna check is that two symplectic manifolds, and that's a theorem of Darboux. I'm going to give first the cool statement and then the classical statement. Any two symplectic manifolds of the same dimension are locally symplectomorphic. Okay, of course, no way Darboux stated the theorem as such. So let's do a reloaded version, like this is the reloaded version, if you want, in the current language. And I'm going to state it in the following terms. That's the classical version. It's the same statement, but of course, no way Darboux would define it like this. Okay, and the classical statement is that given a point P on a symplectic manifold, there exist local coordinates You're going to be surprised by my choice now, but it's in part inspired in the momenta position example of my previous video. I'm going to call these coordinates x, y, y. xi, y. Okay, so let me be more precise here. I'm going to erase this. And I'm going to pay attention. I'm going to put the dimension of the manifold. I'm going to say that this has dimension 2n. And then I'm going to pair x1, y1 to x and y, such that in a neighborhood of P, omega can be written as omega sum of dxi dyi from I equal to 1 to n. And classically, this expression is called Darboux symplectic form. Indeed, it's the same Darboux symplectic form we saw in the cotangent bundle. So one remark I want to make, and I don't think it's too late to make this remark. We saw this before. Two remarks. We saw omega on the cotangent bundle of M in previous video, in the previous video. And now I can indeed now I can say, look up in the screen on the right, and precisely now I'm gonna link the video so you can recover it. It's great, YouTube. Okay, and the second thing I want to say is that yesterday, today, the previous video, I didn't talk about the zero baby super example, which is I can talk about symplectic vector spaces. And I don't think it's too late now. If you look at my notes, that's the way where I start. I talk about symplectic vector spaces, I talk about symplectic basis, I prove everything step by step, but now I'm just giving, like, I'm going back to that part. In the notes, you'll find it at the beginning of the chapter, all right? So let me talk about symplectic vector spaces for a second. And I just want to leave this as an exercise. Indeed, it's an exercise in the list, that if you have a vector space, and you take its dual, then you consider the direct sum of F with its dual. This is again a vector space. If this has dimension n, this has dimension 2n, of course. So the exercise I leave to you is to check that the form is skew symmetric and non-degenerate. And for vector spaces, this is the same as saying that this skew symmetric condition is the same as saying it's a constant form, all right, and that it's non-degenerate. This is exactly equivalent to saying that omega is a symplectic form. I want you to think about this example. On the vector space B. So this pair is an example, it's a baby example of symplectic manifold. And indeed, for linear algebra, symplectic manifold, and I want to link this example with the Darboux symplectic form, and indeed with the cotangent bundle, because it's just from linear algebra. Given omega a symplectic form on a vector space, so in the sense that I have a skew symmetric form, non-degenerate, then there exists a symplectic basis. This is linear algebra. And what does it mean, a symplectic basis? It means that I have a basis E1, En, F1, Fn, such that omega Fj is delta Ij, and I have like two pairs of vectors, okay? And omega on the same kind of vectors vanishes, and omega on the same kind of vectors, Fi, Fj vanishes for all Ij. All right, that's what we call a symplectic basis. And that's a fact from linear algebra that maybe you did when you were studying linear algebra. Maybe you didn't, but you can try to prove this by induction. It's an easy exercise. And in this induction, if you write this vector in coordinates, if you have this V symplectic vector space, and you write and you choose as this symplectic basis any vector, it's going to be written as the sum in these coordinates from in this basis in some particular coordinates. Okay, I take the symplectic basis and I can always write it this way. And if I take another vector x prime, I will have an expression of the sort xi prime ei plus yi prime fi. So when I do omega xx prime of these two vectors, what I get, I put vectors, so you see this is a vectorial space. And if you do this computation just from the definition of symplectic basis, then you get that this expression is just xi yi prime minus xi prime yi. All right? Indeed, well, this is just to say that we can write this omega as the differential form constant with constant coefficients of this sort. And this is how you connect Darboux symplectic form to the symplectic form on a vector space via symplectic basis. And I wanted to explain this is in the notes, but I wanted to explain this because this is useful for a clear proof of Darboux theorem, okay? Which I'm going to do now. And now I'm going to prove Darboux theorem, okay? And I'm going to do this proof in red, proof of Darboux theorem. I'm going to go and prove in the, well, it's the same language indeed, that one way or the other, it's going to be the same language. Okay, so I'm going to prove this of Darboux theorem. And I'm going to use the existence of this symplectic base. This is going to be important. If you look, well, if you want, this is a sketch, complete proof in the notes, okay? Then the first thing I can observe is that I have my symplectic form. So I want to do a first observation that using the exponential map with respect to a Riemannian metric G, okay? Using this exponential map with respect to the Riemannian metric G, we can always identify a neighborhood of P with a neighborhood in the tangent space. This is why, because the exponential map, now I'm thinking of the exponential map in the most practical way. It's a mapping that goes from the tangent space. Thinking of geodesics, you take a Riemannian metric, the exponential mapping, you choose a direction to compute the geodesic, and you take the geodesic at time one, and this is a local diffeomorphism, right? And sometimes it's convenient to think of a neighborhood of a point like a neighborhood in the tangent space. Why I say this? Because if M is symplectic, I may consider the tangent space at M, okay, which is also going to be a symplectic vector space. And I may consider a symplectic basis here. Of the vector space, okay? E1, F1, En, Fn, and you can take, when I say take x1, y1, xn, yn, symplectic coordinates in that symplectic base. So on the one hand, on M, and look that here I'm using the inverse of the exponential mapping. Now this went up. This went up. One sec. We are going to the right point. Here. Okay, exactly. So if I do the inverse of the exponential mapping, all right, I'm in tangent space, and then I take this coordinate on tangent space, and I push forward and back these coordinates. So I'm just identifying a neighborhood with the neighborhood of a tangent space. If you look at the nodes, you have here the exponential, the inverse of the exponential, and you get lost after a while. And now I take these symplectic coordinates in that symplectic base, and I take omega 0, thus the constant form. That I'm already considering this constant form. I'm writing this in the neighborhood of the point P. Okay, in M. So I'm identifying with exponential map this this expression on the tangent space, okay, with the neighborhood. You agree? And then I have omega 1, which is omega, is the form, the symplectic form I have on my manifold. Well, there is a minor detail that is symplectic form. I'm going to assume, I can assume, because otherwise I do a change of coordinates here. I can assume that omega 0 at the point P is the same as omega 1 at the point P, because omega 1 at the point P, it's constant. Okay? And I assume the constant is the same. I can always do this by doing a change of coordinates. Okay? So that's important. And now Moser enters in. That's important. Now Moser enters in an important way. The following is called Moser's. I say Moser, not Morse. It's different. One is Morse, the other one is Moser. Sometimes both of them are used in the same context. So, especially in symplectic geometry. So I'm going to talk about Moser's path method now. What I'm going to do a very clever thing due to Jürgen Moser, which is the form omega 1 to omega 0. And I'm going to do this using an homotopy. How genius is that? That's great. So what I do is to take a path of forms, of symplectic forms. I need to prove that they are symplectic. I take omega t. I want to be, when time is 0, I want to be in omega 0, okay? So what I do is 1 minus t omega 0 plus t omega 1. All right? Okay. Okay. I do this combination. Observe that when t equals 0, I'm omega 0. All right? And when t equals 1, I'm omega 1. Okay? Okay. An interesting observation that this omega t is closed. Well, that's trivial because this is I can write it like this. And omega 0 is, of course, closed, and omega 1 is closed because omega 1 is omega 0, therefore it's a symplectic form. Okay, so this is a path of closed forms. And why omega t is symplectic? That's an interesting thing. Well, I have to check that it's non-degenerate. And the interesting thing is that in a neighborhood of a point, that this is true for omega 0 and omega 1. Why is this true for the path? That's something I want you to think of. Exercise. Check that the condition, and the reason is that the condition of omega t to be non-degenerate is an open condition. Therefore, you can check that, well, you can cover this from 0 to 1. You can find always a smaller neighborhood such that this is in all the, for all t, such that omega t is non-degenerate. Therefore, omega t is symplectic. Great. I have a path of symplectic forms. The great idea of Moser is to consider the following equation. I'm going to put this in red because I find this very important. Okay, Moser consider the following equation. Well, he contracted, this looks quite like Hamilton's equation, okay? And you have to look at the path of symplectic form. You want to find xt, and now we have to decide what we put here. But omega 1 and omega 0, okay, they are on the same symplectic class because we are in a neighborhood of a point, and of course we know because of Poincaré's lemma that this is the differential of beta, okay? Omega 1 minus omega 0 is the differential of beta. Okay, then the thing I put here is minus beta. That's the equation we consider. Let me erase this here. Let me put this bigger. Today it's not my day. So this is what it's called, Moser's equation. Okay, and the thing is that omega t being non-degenerate, this implies, and beta is the beta that you get from this other equation here. You plug it there, and because omega t is non-degenerate, for a beta, you get unique, there exists a unique x sub t. That it's a vector field that it's t dependent. Why? Well, because omega depends on t, okay? And now what you do is this vector field, you take the flow, the t-dependent flow of the vector field, which is the vector field satisfying this equation when t equals 0. Okay, let me be formal. Let's put this, let's erase this here. Okay, let me do this. Well, this is totally necessary. I don't know what's the notation I put, but when s equals t. Okay. So I look at this equation here. Okay, and that's the equation I consider. Okay, so I take the t flow, I take a flow such that different xt over phi t is the differential of phi t over t. This usually, well, in the notes, I think that I put this as d phi t as xt phi t d phi t dt. That's it. I think I put, this is the same, okay? So that's the flow we are considering, okay? And now what I need to check, and that's going to, well, I'm going to do the proof. I have to check that if I take this flow, that I have the following condition, phi t star, that the pullback gives me omega 0. Let me prove this. For this, I need to use a formula, which is the derivation of t. I could do the S game here, but I'm going to be like, I'm going to go straight. If you look at the notes, I use the S and the T here. I'm going to prove, this is proved in the notes, okay? That's in the notes, look at notes. That you may do this derivative in two parts. This is where you have dependence, you have the derivative omega t with respect to t, plus the derivative of xt omega t. All right, now you do phi t star, and now, well, what is the dependence of omega t over t? Omega t is the path 1 minus t omega 0 plus t omega 1. Okay, so if you look at this dependence, you get exactly omega 1 minus omega 0. And now I need to look at the second term, which I'm going to mark here, is I need to check what is this integration mark. This is the derivative of xt omega t. Now I'm going to use Cartan formula. Cartan formula is in the notes. When we explain differential forms, I think we stated this, of course we didn't prove it, okay? And Cartan's formula, I'm going to put this is a very important formula. Just for the ones who don't know this, I'm going to put it here. Relates the derivative with the differential and the contraction. It tells me that such a formula holds. That's Cartan's formula. It's so important that in some books you call it Cartan's magic formula, which looks like a magician. So I apply this formula here, okay? So when I apply the derivative of this formula here, what do I get? I get the differential of, okay, let me go back to the color. I get the differential of, what was this color? It was this blue, I think. So I get the differential of ext. Well, this is the contraction. I write it like an I, but this is the contraction, of course. Ext of omega, okay, plus the ext d omega. Now omega is symplectic, therefore this goes to 0. Therefore this is the differential of ext of omega. But from the equation, from Moser's equation that we have here, okay, where I am, sorry, I am losing where I am. Okay. Well, from Moser's equation that you have up there, I'm sorry, because this computer is betraying me and I'm losing the formulas. From the formula that you can go yourself, go up there and check the formula, or look 3 minutes before or 5 minutes before, okay? What you get here is exactly minus beta, okay? So this is minus the differential of beta, but minus the differential of beta is precisely omega 0 minus omega 1 from the definition, because omega 1 minus omega 0 was differential of beta. Therefore, we plug this thing up there. Sorry, this disappeared. Formula disappeared. Little bit of patience. Okay, so, well, okay, I'm gonna write here, plugging the formula, we get up there, we get that the differential from t of phi t star of omega t, okay, was phi t star of omega 1 minus omega 0, and now we have plus omega 0 minus omega 1. So this is 0, okay? So this means that phi t star omega t is constant because its differential is 0. Therefore, for t equal to 0, we have that this is omega 0. Therefore, we have that omega t, if you evaluate at this part at t equals 0, phi 0 is the identity because it's a flow, okay? So this is equal to omega 0. And this ends the proof of the theorem, and this proves Path's method. Now that I have Path's method, I'm going to end because this is starting to be a long video, with a corollary of the path method, which is Theorem 2. Theorem 2, which is the global classification of symplectic surfaces. So this is a theorem by Moser. And this is where Moser introduced this path method. So I'm going to use exactly the same method. The proof is exactly the same, just paying more attention in one thing, okay? That let M1 omega 1 and omega M2 omega 2 be two symplectic surfaces then if the symplectic class is the cohomology class is the same, then they are equivalent. Indeed, this is an if and only if, but with the path method, we can prove this equivalence. The other equivalence is a bit hard, but we can prove it too. Then they are equivalent. It means that there exists a flow such that takes omega 2 to omega 1. And that's a global classification result. So this means that in dimension 2, the only global invariant is the symplectic. My computer is going nuts. Have to be patient. And I don't know where I'm writing. Okay. The only global invariant symplectic is the cohomology class, the RAM cohomology class. Of omega. How the proof works, I'm going to sketch it. I think I have it in the notes complete. And the sketch is the same, play the same game. So play Moser's path method. But now there is some reasoning to do, which I'm going to leave as an exercise, but I'm going to point at it, that if you have these two classes, you use that they are on the same cohomology class to say that omega 2 minus omega 1 is the differential of a certain beta. So you play the same, okay? It's convenient maybe to talk about omega 1 to rename omega 1 and omega 2, but you take the path, the linear path, and you look at this equation. There is a thing though, because how do you check that omega t is symplectic? Well, this is because you have two forms, and because you're in manifolds of dimension 2, and you have that the area form, you can add up the area form in a convex way. Okay, so that's quite an exercise indeed to check that this is symplectic. And the second important issue is the integration of xt, that I didn't say anything before, because locally you can always integrate. Well, this is a bit of a lie. You need to check, for instance, that you can integrate locally, but it's easy. But that you can integrate globally, you use that that the manifold is compact. So here, the theorem is true for compact surfaces, which I don't know if I wrote in the statement. That's important, that I need to have compact surfaces because I use it. And for non-compact surfaces, you can have also some results, some partial results, or for surfaces with boundary, you may have, I mean, you have other results of classification, which are very interesting. Okay, so I'm very happy because I give a complete proof of Darboux theorem, which is like something that I'm not always I can do. And I sketch here, that's the 2 steps, and then the method of the proof is the same as Darboux theorem to prove that phi star omega 2 equal omega 1, because you take phi equal to phi t, and omega 2, you call it omega 1 tilde, and omega 1, you call it omega 0 tilde. And you do the standard linear path, and you look at this equation, all right? That's what you do. Okay, I'm super happy about this video. I think, well, I shouldn't say this, but I proved quite a lot of things. I proved local classification, and I even gave global classification dimension 2 by a theorem of Moser. This is pretty cool. So we're gonna stop here, and in the next video, I'm going to in the next video, what I will do is to talk about Hamiltonian vector fields and Noether's principle. I think that you will like it. So stay tuned.